Before we start the next talk, there's an announcement. All the challenge participants who are going to be here next week, please stay back after the last talk today, because we'll be giving you your laptops that we'll be using for the challenge. If there are people who are not there, please inform them to stay back after. Should we wait for some more? No, they have to be present because there are some formalities. Raj will let you know. Yeah. All right, so next speaker is Teja Tulabandula. He is a research scientist in the machine learning and statistics group in the analytics lab here. He has a bachelor's and master's from IIT Kharagpur, where he received the President's Gold Medal. And then he went on to Massachusetts Institute of Technology for his PhD, where he was a Xerox MIT Fellow and a Fulbright Scholar. His research interests are in several areas: artificial intelligence, machine learning, optimization, decision making, and sports analytics. And apart from research, he has also worked for a hedge fund, a smartphone manufacturer, an institutional asset manager, and a semiconductor company. Thank you, Teja, for today's talk.
Thanks. So hi everyone, my name is Teja, and so today we'll have a very interesting session on something called online learning. I'm hoping that the session is going to be a bit interactive, so we'll learn together. So online learning, so credits to some course notes by Percy Liang at Stanford, and a survey paper by Charlotte Schwartz. Okay, so the outline of this tutorial is going to be as follows. We're going to just introduce online learning. So forget about everything that you learned about machine learning for now. So we're going to start from absolute scratch. So online learning is going to be introduced, and after that we're going to talk about something called online convex optimization. So you've had a tutorial on a little bit information about You've seen a little bit of convex optimization, so we'll use a little bit of tools from there. One of the main features in this subfield is, people want something called regret bounds. So we'll have a look at them, and then finally, if we have time, we'll look at one particular setting called the multi-arm band setting. So the main tools will be probability and convexity. Not too much in probability actually, so you don't really need to know much. Okay, so so what are we going to look at? We're going to look at the prediction setting. So basically, as you know, a prediction setting is we want to somehow come up with a map which maps from x in some domain x to a range y, script y. So the map is what we want to get at. But the online learning setting is as follows. It's actually a game between a learner and the nature. So the nature is going to provide you this input instance or feature vector or whatever. It's called xt to you. We're going to make some prediction pt, and then we're going to receive, we're going to see the truth, which is yt. So those are the three arrows, and basically the difference between online learning and batch learning, as in empirical risk minimization or SVMs or the stuff that you do regularly, is that you have to kind of predict on the fly, and so training is interleaved. You make a prediction, you get the truth. Again, in the next round, you make another prediction for another instance, you get the truth, and so on. The question is, should we train, let's say, an SVM in each round and make a prediction? So, you start from, let's say, an initial SVM model. Okay, you build that model using, let's say, some historical training data. Okay, you did cross validation, everything is nice, and you got the SVM model. You get a new instance xt. You're going to make a prediction pt using the SVM model, and you'll get the feedback. Now you'll add this xt-yt pair into your data set, and again, do this training, validation, and come with a new model. Should you do that, or should you do something different? Is the question here. And the way I've really introduced pretty much nothing here, in the sense I've not said anything about distributions of x or y or anything like that. So what is the notion of goodness of the learner? When is the learner actually learning is another question. So we'll hopefully through this journey we'll see that okay, maybe we should not resolve SVM or whatever random forest or deep network every round, but we should do something different. So one of the crucial ingredients in online learning will be something called a fixed set of experts. So these are fixed set of maps, So in batch learning, you're trying to learn a model, right? Let's say you're just doing regularized regularized least squares or something. So your set of experts will be just the set of vectors in some let's say 2-norm ball. So something similar is happening here. So we'll have a set of experts, and we are the learner. So we are generating a sequence of predictions PT. Every expert in my set of experts is also going to generate predictions for every input instance. So now I can quantify something called regret. Okay. So regret is going to be just the cumulative loss incurred by me in every round. So over a period of t rounds minus the loss incurred by a specific expert H. Okay. And then regret is that's regret per that's regret with respect to an expert, and this is regret with respect to the set of experts. It's just the max of the those regrets that you can compute per expert. So this is how we're gonna try to measure the goodness of a learner, and hopefully this regret that I've defined here, this objective measure is going to be small. Hopefully doesn't grow linearly as a function of a number of rounds and so on. So that's what we're going to see. So as you saw in the first, there are only 2 slides here, you saw that I've not really introduced any notion of a distribution. There's no expectations floating around, nothing. So basically this is called the adversarial setting, and you can ask, why can a learner L compete in an adversarial setting such as this, or should the okay. So this question leads to a few sub questions, which is how strong is my adversary, as in how strong is the nature? Can nature generate XT instances in a very clever way, and so on. So those are the questions you can ask here. We'll see. We'll address this question in a couple of examples later on. Okay. So L's objective is to minimize regret. That's low regret, low R value is good, and sometimes so for example we may want it to be sublinear in the number of rounds. You can ask, can regret be negative? Given just 2 slides, okay, a learner is there, he's picking some predictions. Do you think this can go negative? What do you think? Let's say the learner just picks one expert at the beginning of time and just plays that just copies that expert's predictions. Okay. Then do you think that learner's regret can go negative or not? I can see some partial answers, but okay. So so it of course depends on the learner, right? The learner is not constrained to pick. Okay, I didn't say anywhere that the learner has to pick an expert from the set and only copy him or her, right? So in the situation where they copy one of the experts from the beginning of time, then of course it cannot be negative because because of the definition they have defined regret. But let's say the learner kind of switches between these experts, then he's actually creating a new expert by himself. He is becoming an expert. So maybe his or her regret is going to be less than 0. So okay, let's look at a particular example. Let's say my class labels are -1 and +1, and let's say I have a 0-1 loss. So it's an indicator of whether the prediction is equal to the truth or not. And let's say the learner is deterministic. Okay, so I'm just coming up with some settings of this game between the learner and the nature. So let's say L is deterministic, and let's say the adversary actually knows L. In the sense, what does knows L mean? Okay, the adversary knows how the learner is going to play. So pretty much the algorithm, the deterministic script by which the learner is going to play this game. Okay. So this is a setting. We can make the following claim. That is, there exists a fixed set of experts and a sequence of xt yt's which nature generates, such that the regret is lower bounded by t by 2. Okay. So let's pause here and think. Regret is lower bounded by t by 2, which means the learner is actually not even learning anything. Okay. In the sense, he's making a lot of mistakes, incorrect predictions, and the predictions are just, you only have to pick +1 or -1, and even in that, if you're wrong greater than half the time, in t rounds you're making more than t by 2 mistakes, then something's pretty bad here. That's what I mean here. So let's try to come up with a proof of why this is true, or an example. So let's just show a particular fixed set of experts such that regret is lower bounded by t by 2. So let's say since the adversary knows the learner, which means that the adversary can always pick the ground truth to be exactly different from what the learner is going to pick. So that means that the learner's loss is going to be t. Okay, in t rounds, always every round is going to make a loss, so his loss is t. Let the set of experts be h minus 1 and h plus 1. So where h minus 1 means that expert is predicting always -1. Okay, and h plus 1 means that expert in the set of experts is always predicting +1. Then it's kind of very simple to see that the total loss incurred by both the experts is equal to 1. One of them is going to be right because there are only 2 labels, which means that one of the experts must achieve loss less than equal to t by 2, because you're summing over such t such terms. Okay, which means that the other expert is going to have which means that one of the experts has loss at most t by 2, and your regret is defined as the difference between the learner's loss and the worst case expert. So this guy is let's say we pick this guy, then t minus t by 2, which means that you're lower bounded in regret by t by 2. So that's what's happening here. So in the sense, I wanted to give you this example to give you an intuition that here there's really no learning because you're deterministic. Okay. I mean, or maybe the adversary is too powerful. Okay. So let's go to the other extreme. Let's look at another setting. So let's weaken the adversary. In particular, let's assume that how are we going to weaken the adversary? Let's assume that we have an expert H star in our set of experts, such that they are always right. In the sense, there is an expert in your set of experts who is always right, and you just have to, if you knew it a priori, you would just copy that guy's predictions, and then you would have zero, loss, in t rounds, right? Because that expert is not really making any errors. Okay, this is t is equal to 1 to t. So here I've written down in 3 lines a particular learner. Okay, in this case the learner is still deterministic, but you'll see that the learner's regret is better. So let's say the learner maintains a set Vt. Okay, so let's say the learner maintains a set Vt, which is going to be the set of all experts who have until this point of time, let's say till the previous round, t minus 1th round, have incurred 0 loss. So they're basically consistent on the previous t instances seen so far. Okay, and then given this internal data structure or the internal set that the learner is maintaining, they'll predict pt as the majority over the predictions of experts in your set. And then the way they're going to update it, they're going to see the response, whether they're right or wrong. Okay, and then and let's say we are still in the binary case, which means that let's say if they're if they are right, there's really Okay, I guess this next update is anyway doing what I'm going to say. So the way you're going to update your set is you're going to just augment all the experts who have been right in this instance. So there will be some experts who will be right in this instance, and maybe some who are wrong. So you're going to just retain the ones. You're going to kind of shrinking the set VT from VT to VT plus 1. Okay. So a simple analysis. So, basically we want to come up with simple algorithms, and we want to come up with simple regret bounds. So here's some analysis. So let's say we are in round T, and we make a mistake, but we took the majority of the predictions by our experts in the set VT, which means that greater than half of the experts in the set VT are incorrect in this round, right? Because we took the majority. So we're going to eliminate these many number of experts in our set in this round. Okay. So you can see that on each mistake. So in rounds when there is no mistake, you're not really doing anything. But in each round that there is a mistake, you're kind of shrinking the set VT by half. Okay. Which leads to this, this inequality. We know that there is going to be at least one consistent expert. So the size of VT cannot be smaller than, cannot be an empty set at any given round, let's say round T plus 1. And we know that the size of VT is going to be less than or equal to, let's say we started at the beginning of the day, at the beginning of the rounds, we started with everybody in my set. And let's say we have made some number of mistakes. So this is number of mistakes. That means we have shrunk the number of guys remaining in the set VT plus 1 is going to be, okay, kind of T dependence have skipped in a couple of lines, but so the size of VT plus 1 is going to be upper bounded by the size of the original set and the number of times you made. Okay. Number of times you made mistakes as in wrong predictions. And second thing you can see is that regret is equal to the number of mistakes. Why is that? Yes. Yeah. So one of the experts is is always making zero error, which means that over T rounds, if you remember the definition of regret, the second term included performance of an expert. So if you pick that really good expert, then the second term is actually 0. So the number of mistakes is just equal to the number of is equal to your regret. So that's straightforward to see. And then you just pick the first and the last inequality, and you get this bound. Regret is upper bounded by log of the number of experts that you have. Okay. This is great. I mean, in the last setting we saw that regret is lower bounded by T by 2, and here we are seeing there is no dependence on T. Okay. In the sense, I mean, regret at time T, let's say, I've skipped, but the right hand side is not dependent on T, which means that it's a constant. So after log cardinality of h number of rounds, you actually have zoomed in to the right expert. That's all. That's what has happened here. So per round regret, if you divide R by T, is going to 0 as T tends to infinity. So essentially, after a large amount of time, you have figured out, you have learned, in the sense you will no more make any more mistakes, from that round onwards. In fact, from round T plus 1 onwards, which can be related to this. Right? But our assumption is too strong. We said, okay, one of the experts is going to be always right, God or Oracle expert who's going to be always right on, in terms of their prediction. And also, the second thing is you can see that the bound is useless when the number of experts is infinite. Okay. Why should I choose a finite set of experts? Like in linear regression, I said each point in your L2 ball, let's say you're constrained. Your linear regression is all about searching for a vector W in some set, right? If you do a regularization, L2 regularization, all it means is that you're searching for a point in an L2 ball. Okay, that ball is not finite, right? So we can't really, so there's some discord here. So these are a couple of examples of online learning, and we're going to come up with some algorithms which are more general than what we saw here. So we only saw one kind of interesting, some majority based algorithm. But we're gonna make the set H infinite and so on, and then we're gonna come up with more interesting algorithms, which are still much simpler than the algorithms that you see in supervised learning or any other field of many of the other fields of machine learning. So for that, we'll take a course and talk about something called online convex optimization. Okay, it's first of all, you may say I have not really mastered convex optimization, and you're going to talk about online convex optimization. Well, the only property we are going to use is there are several degrees of information you know about in terms of your toolkit about convexity may involve a lot of things, but here we will use some of the more elementary tools. Okay, so what is convexity in a nutshell? You had a full session on this, but the intuition that you have to develop about convexity is this. Convexity with convexity, you can say something about the global behavior of a function, okay, by something local and simple, which is a linear function. So what do I mean by this statement? What does convexity bring to the table? So here I've drawn, let's say, a very simple function, and I've pointed 3 points, u, w, and v. Okay. What I'm trying to say with this statement is that the global behavior of the function f, which is curving like that, can be quantified by something local. Let's say we localize to a point w. Okay. The statement that we can make is that a linear function, with intersection at w, a linear, let's say, hyperplane or something, actually is a lower bound for the function itself globally. Okay. So that's the intuition for convexity. So you can pick a point, any point on the convex function, okay, and you create a particular linear function. Okay, basically you take the gradient and you create a linear function, and that function actually can actually lower bound your function all over the place. At every part of the domain. That's the cool thing. Here I've just written the definition of what is known as the subgradients, set of subgradients, which is just that if the function is not differentiable, then you may have a lot of gradients at that point. So you can pick any of those gradients, and that's the set I'm describing here. Okay, so that's it, convexity in a nutshell. So how are you going to use convexity? We'll actually see that 20 slides from now. So right now we actually really don't need much of convexity or probability theory. So what was online learning? I said there is essentially 3 arrows between the learner and the nature. It's a game, right? So the nature gives xt, the learner kind of makes a prediction pt, and nature responds with the true label yt. Okay. So what is online convex optimization? It's also a game. Okay, it's a different game where there's a learner L prime and there's nature prime. Okay, which is different. Let's say. Basically, and it also works in rounds. So it's a game. In round T, the learner is going to output an object Wt. Okay, it could be an expert, it could be something, whatever it is, we're going to see. And nature is going to respond by giving you a function. Okay, it's going to give you a function, and that's it. And so there are only 2 arrows here. You're going to give a vector Wt, and nature is going to respond by giving you a function Ft. So online convex optimization I've just written as OCO as short. So L prime chooses Wt in some set S, okay, and nature prime, okay, L prime and nature prime. So nature prime chooses Ft, which is a function from that set to let's say the real numbers. Okay. In online convex optimization game as well, I can define something called a regret, which is going to be very similar to the regret we define in online learning, which is the sum of the difference between the evaluation of Ft on the point that you picked before actually seeing Ft minus a particular fixed point in that set S. Okay, U is some point in that set S. So this is the difference, and regret over that set S is going to be the maximum of the previous regret, which is per point over the set S. So this is what I call the new regret in this particular game. Okay. So here set S you can think of as a set of experts, and also the set of and also the choices that learner L makes. So L WT from the set S, and you're also comparing yourself with U, which is a point in set S. Okay, so basically what we are trying. So I just introduced online convex optimization. What we are going to do is first relate it to online learning, okay, and then also relate it to convex optimization, because we kind of roughly understand convex optimization from doing supervised learning, solving supervised learning with different techniques like SVM and so on. So let's look at the first relation. So given, so let's say XT and YT are not really in the online convex optimization world. XT and YT are in the online learning world. So given XT and YT, what we can do is we can construct a convex function FT, which is parameterized by XT and YT, and then we can somehow get into the online convex optimization world, where we kind of aim to get low regret, so that low regret for the OCO learner L prime implies a low regret for the online learning learner L. Okay. So how we do this is I'm going to illustrate using an example. Okay. So let's say we have so let's think of the online learning world. We had, let's say, D experts. Okay. And again, as in the previous online learning setting, let's assume we have a 0-1 loss. So it's just we just count whenever our prediction is not the same as the truth. Okay. So the way we're going to introduce the online convex optimization world into this is as follows. Okay. Let's create a learner L prime who produces WT from a simplex. Simplex, which I'm denoting as delta subscript D, is going to be a simplex over H. So what does it mean? I have D experts, right? So I'm going to think of a D-dimensional simplex, and I'm just going to call that my set S. Okay, and now I'm just creating this online convex optimization learner who's going to start spitting out points on the simplex. Okay, and then how I'm going to couple this online convex optimization with the online learning setting is that we're going to sample from this distribution. So since it's a point on the simplex, it's a PMF essentially. Okay, so we're going to sample from that WT and choose the prediction according to the expert that is picked. So essentially, okay, the point is WT is a distribution for experts. So if you sample from WT, you will get and I essentially it's like picking an expert from the it's like picking an expert. So once you pick an expert, you can just copy his prediction. Okay, that's what it's saying. Also the expected. Okay, so we just at least figured out the first part of the online convex optimization world, which is how the learner generates WT and how it relates to the online learning world. Okay, now the online learning world is gonna have XT and YT, right? So we can now define basically a function. There has to be a function which goes back to the learner, right? So we can define the function as a linear function, which is the expected 0-1 loss of WT. So I'll show that in the next slide with pictures. So hopefully you can get some idea. So this is what I explained. So let's say there's a nature over here which I have not drawn as a blob. Nature gives XT, and there is an online convex optimization learner who is generating WT. From WT, we know how to generate, how to pick an expert. Let's say H of JT, where JT was drawn from WT, and we just copy their prediction and just give that to the nature. Nature is now going to respond with the true label YT, and then what I'm saying is we have to complete this part, which is the function that needs to be passed to the online convex optimization learner. So that function is going to be parameterized by ZT, where ZT is the loss of every expert in your set of experts. So basically you have D experts, so plug in each expert on the right hand side of your loss function, which is a 0-1 loss function. YT is given by nature, so you can kind of get this vector in every round. Okay, and you're just going to call this function as W transpose ZT. That's it. That's the function. Okay, and first of all, okay, so couple of things. This loss function need not be a 0-1 loss function. It can be any loss function. Why is that? Because in the online convex optimization world, you have to be convex with respect to W. So irrespective of what loss function you pick, your function that you're passing to your learner is essentially just a linear function, which is always convex in W. Okay, so the loss function is really not affecting convexity in any way. Okay. And also note that we kind of had to have finite number of experts here. So basically this kind of is supposed to give you an idea of how online learning is related to online convex optimization. In the sense, if you're faced with an online learning problem, there is potentially a way to map it to, you can call a subroutine, which is an online convex optimization solver. So you can come up with good learners here and somehow try to get low regret on this side. Okay, so that's the point here. So let's kind of relate online convex optimization to just convex optimization. Okay, so what is convex optimization? Just think of this very simple math program. You're trying to minimize f of w, where w is a point that you want to pick from a convex set S. So f is a convex function, S is a convex set, and w is a global minimizer. Okay. So we're going to relate it to not general convex optimization. We're going to relate it to machine learning convex optimization problems. So in ML, what happens is that typically this objective function is just a sum of many convex functions, because typically think of n as the number of training examples. So you'll have 1 by n sum over some other function, some other function of the parameter. Okay, so this function is going to be dependent on that particular example or row, xt x by I, for example. That's all. So the way we're going to relate is relate just machine learning convex optimization to online convex optimization is as follows. So at each round t, we're going to choose a particular function gi, which essentially means in your training data set, you're going to pick one particular training data, and you're going to what the function that corresponds to that training data is. You're going to pick that at random, and then give it to L prime. So L prime is still the online convex optimization learner, which essentially what I'm saying is I'm trying to define ft. L prime was supposed to get an input which was ft. So I'm just trying to define ft as a function g of it, where it is drawn uniformly at random from n training examples, right? Okay, and the forward part is clear. W is the W that the online convex optimization learner picks is the same W that is there in the machine learning objective. The decision variable of the machine learning convex optimization problem is the same W that L prime is also dealing with. Okay, so we have defined both arcs of that online convex optimization game. Okay, so let's say after t iterations, I have a learner. Let's say, okay, it has some regret. Let's forget about what that L prime's regret is. Okay. Let's say there is a learner who is able to generate a sequence of W's and is able to get a sequence of functions. Okay. Let's say this happens in t iterations, and then after t iterations, let's just call W bar to be the average of all the points that are picked from the convex set. Okay. Okay. So let me define this W bar. What I'm going to claim now is that W bar is related to the global optimizer of your convex optimization problem, W star, via L prime's regret R. So every learner in the online convex optimization world is going to always come with some regret guarantee, right? Either the regret is really bad or the regret is really good. Some number R, okay, which is a function of t. This learner was used for t rounds, okay. I don't know what the learner learned or did not learn, but he or she did generate a sequence of W's. Okay, so I'm going to create this averaged W, and I'm going to say I'm trying to relate W bar to the global optimizer of the convex optimization problem. And basically the implication is as follows. So why am I trying to relate W bar? Why W bar? Why not something else that we can see later? But the implication here is that if the regret of the online convex optimization goes to 0 fast enough, then W bar is essentially trying to solve the convex optimization problem, okay, the original convex optimization problem. Okay, so let's actually do the relation, because so this is kind of important when you're trying to use, for example, stochastic gradient descent or something else, right? Which kind of work per example rather than work compute gradients over the entire training data set. So what is regret? Okay, so what is regret? So as I said, the online convex optimization learner is playing in the same space, the same set S over which you are supposed to optimize your convex optimization problem. Okay, so let's find regret with respect to W star. Who's the goal? Which is the global minimizer? So regret, as I said, is just defined as this way: is the sum over T rounds of evaluating the function which was given by the nature over the WT that you picked minus the function that was given by the nature at that expert, W star. Okay, that's just a definition of regret. So just let's rearrange. Okay, so should I do the board or no? How many people are interested? Okay, so let's see. So basically, regret at W star is equal to the sum over T rounds of Ft of Wt minus Ft at that particular expert. So this is the regret of my learner. Okay, actually I'm hiding the dependence on learner, but this is a regret which is a quantity which is a function of which depends on the learner. So this is what the first statement is. So I just divided by T basically. Okay, I rearranged. Basically I sent. So I just rearranged in the sense I left this term in fact I just flipped the rearrangement, but just think of pushing this term to the right hand side. Okay, so basically I get sum over Ft of W star 1 by T plus R by T is equal to sum over Ft at Wt over T 1 by T. So this is what the second statement is, except for you need to take expectations. Okay. So why take expectations? Why did suddenly probability come into the picture? By the way, we never even touched anything to do with distributions or anything till now. Why take expectations? Is there some randomization happening in this previous slide? There's something happening here, right? Yeah, other than that, there's really, learner is kind of oblivious to you. It's a black box. So, okay. That's why we take expectations. So the expectation is over so f of t is a random quantity. So your regret is actually a random quantity because f of t is actually in every round out of n data points you're picking one of the functions, right, uniformly at random, and you're setting that to be f of t. So that's why f of t is random, and so regret is random here. Okay, you're taking expectations. So the first thing we're going to do is so we'll show two things. One is we're going to take the left hand side and get a lower bound for the left hand side, and the right hand side, the first term, we're going to get an equality. Those are these two lines, and based on that we can get an idea about how W bar, which was just average of a bunch of points that your learner provided, how that is related to the global optimizer of your convex optimization problem. Okay. So to get the first inequality, okay, let's so how do we show this? And WT, but on the right hand side there is W bar. Okay, at least we know that W bar is equal to, I don't know if these guys can see. You can't see, right? So W bar was just 1 by T of sum of WT. Right? Yeah. So W bar we know how it's related to WT. Okay, but F of T, how is it related to F? How is it related to F? Remember, F is the objective function of your convex optimization problem. F of T is something which you're giving in the game that you artificially created. Okay. How is it related? Okay. Any ideas? Any thoughts? We know that I just told you that F of T is a random variable because F of T is equal to, is essentially G of IT, where IT was drawn uniformly at random, with, essentially IT, yeah, uniformly at random from 1 to n. So this is not general convex optimization. I said F is actually just a sum of n GIs, okay, and I'm picking one of the GIs uniformly at random, and I'm setting F of T to be that GI. Okay. So do you think this is true? I take expectation of F of T. F of T is a random variable as well, right? I mean, if I take expectation with respect to this, what is it equal to? So what is this expectation? Let's go from first principles, right? We are really, this is equal to, probability of IT is equal to, let's say, J times Gj. Sum over J is equal to 1 to n, right? Sorry, I just am kind of spilling over. So what is probability of IT is equal to J? So what is this? So you remove that. So this is equal to, is it fair to say that this is, okay, I just removed functions here, but at a point, let's say. Is it fair to say that this is equal to F? It is, right? Or it is not. They're only the binary. So yeah, basically this is the relation. So expectation of F of T is equal to F at any point, So basically for all points in the domain. So that at least these two are related and these two are also related. But we want, okay, given that, so how do we lower bound this quantity? That's what we want, right? So can we replace F of T by expectation? Sorry. Okay. What can we do here? Okay. Let's do something. Let's deal with this. Let's start with the right hand side. So what is F of W bar is equal to F of 1 by T summation of WT. That's true, right? I just replaced W bar by its definition, right? Now we're going to use a particular tool that should be in your toolkit, which is called Jensen's inequality. So Jensen's inequality is basically as follows. It works for convex or concave functions, and it's basically saying the function of the expectation of a random variable is less than or equal to the expectation of the function of the random variable if f is convex. Okay. So, but where is, again I've brought in expectations. So where is expectation? This is hopefully some other expectation that I'm talking about. So you can think of the sum as an expectation. With with artificially thinking of 1 by t as the probability, and wt to be the realization of the random variable. So this is think of a uniform distribution. Okay. Then that this guy's expectation is essentially this by definition. So basically we can apply Jensen's inequality, and so we have this. So we can say this, right? So what is this expectation? This is 1 by t sum of f of wt. Sorry, yeah. This is fine. Okay. So now we at least so now we have this intermediate quantity. So we started from okay. So first of all, that expectation over there is because WTs are also okay. Oh no, I said that expectation is with respect to the randomization in the definition of f. But anyway, so we did this. Okay. But this is a statement which is just there is no expectations here. Okay. So let's take expectations on both sides. Now we have to relate, we got at least the left hand side of that inequality. We have some intermediate quantity. We want to relate it to the right hand side of the inequality, which is this. Okay. So how do you think we can do that? We already use this, so we may have to use this, right? What do you think? So can we just replace f by the expectation of f of t? Right? So if we do that, expectation of f of t of wt, and there is a sum over 1 by t. There is our external expectation here. Then we can use essentially another second toolkit that you should know, which is linearity of expectations. You can pull that expectation outside, okay, and that's the right hand side quantity. Okay, so let's look at the second term. So how does the second term hold? Okay, I just gave you the answer pretty much, but why is the second equality true? So it is a fixed point, right? Some point at W star, that's where you're evaluating. You can again take linearity of expectations, as you said, and that's it. So that's how it holds. So we can basically, the end game is this: we are somehow able to relate in expectation the value of W bar with the value of the global minimizer. So this is the optimum of your convex optimization problem, and the regret of the learner itself. So if the learner is able to generate intelligently the sequence of W's, then hopefully the regret is going to be low, and hopefully it's less than it's little low of capital T. Okay, then hopefully this second term is going to die down to 0 as t tends to infinity, and so you're essentially able to match. You're able to get the same global optimizer as you would have if you had if you had solved the convex optimization problem using any of your favorite tools like gradient descent, or what else you do, interior point method, or anything like that. Okay. But you can see here that because of this relation, the rate of convergence is if you ignore this, then it's 1 by 1 by t. Okay, whereas the gradient descent is going to be kind of superlinear. Oh, sorry, not superlinear, but here I've just shown linear convergence, which just means that exponentially you're going to reach the optimum. Okay, so that's the difference between OCO, using OCO to solve a particular convex optimization problem, which involved a bunch of terms, and just solving the convex optimization problem using a technique like gradient descent. But of course, the advantage of OCO based learner is that if the learner's regret is good, you essentially only need one example per iteration, whereas of course the convergence rate is faster, but gradient descent will need all examples, so computation is much more. Okay. And also, second point is that you may not want a really strong algorithm which has really good convergence property like gradient descent even, because you don't really want to optimize f to its global optima. In machine learning, typically the xt and yt's come with noise, so you are fine optimizing it to some point close to the w star. So basically, this is what we've done. This is what we have not done. We have not yet specified an intelligent algorithm for the online convex optimization learner. We related online convex optimization to online learning. We related online convex optimization to a particular class of convex optimization problems. But the key ingredient in the online convex optimization world, the learner L prime, who hopefully has low regret, we haven't yet figured that out. And so we're going to look at a couple of algorithms as time permits, and look at how, what is the intuition behind these online learners, essentially. So we'll look at a couple of algorithms. Forget about the third one and multi-arm bandits. So we're going to look at first algorithm is called follow the leader, and it will have some deficiencies, some positive properties. We'll get some intuition of how the learner is supposed to be designed. Okay, and then we'll look at follow the regularized leader. Okay, and hopefully you'll see some notion of convexity while looking at these algorithms, how they perform. So the follow the leader algorithm is as follows. So this is the algorithm, the learner L prime in your OCO world. So in each round T, you choose a point Wt in your set S, which is just the minimizer of the previous T minus rounds, the function that you have seen. Okay. This is somewhat strange, right? You actually, the online convex optimization learner is calling a subroutine, which is another convex optimization problem, okay, solver, right? But this is how it's going to generate the next point Wt. You may think that this is computationally very burdenful because you're operating per round, and in fact it's exactly like solving your empirical risk minimization problem, supervised learning problem on t minus 1 examples instead of n examples. But we will see that in fact we don't want to use a convex optimization subroutine here. We'll see that later. So basically what we want to do is, so this is the decision rule to pick the next point to give to the nature, okay, before you see ft. So that's why the sum is only till ti minus 1. Those are the ones you have already seen. We want to study the regret of follow the leader, and to make life easy, we're going to upper bound regret u. So this was the term that we wanted a bound over, but we actually are going to find an upper bound on regret u and work with that. So let's say the learner is the follow the leader learner that generates w1 to wt. Our claim is as follows: the regret for that learner compared to any point u, okay, in your that's the comparison expert, which is defined, is just a definition here, is upper bounded by a regret when you compare with the one step look ahead output of FTL. So let's say so Wt plus 1 is going to be the solution of another optimization problem like this, except that you are including the teeth term. Okay, so that's why it's looked at, because you have to get ft to be able to optimize that. And so we're going to replace u with wt, and we claim that this is an upper bound over regret with respect to u for any u in S. Okay, so this is just some simplicity, so we are going to do this trick so that we can understand how it's related to convexity. So you can see that f of t of wt minus f of t of wt plus 1 is like trying to say I fixed f of t, which is a function that the nature gave, and I'm evaluating at two points, wt and wt plus 1, that I generated, and these are successive points that I generated as a learner. Basically this difference is showing, given that function, how much difference is there between my the points that I'm outputting successively. So for example, if wt is at one part of the domain and wt plus 1 is some other part of the domain, you are really, basically your learning is not stable because you're jumping and putting out wt's which are all over the place. Ideally wt should be close to wt plus 1 in some sense, and in this particular sense the difference between their evaluations at ft is small. Okay, so if that is small, then clearly you can see that the regret is small, right? Because that's the term that kind of dominates regret. I mean, that's the upper bound there. So basically, in order to show this, in order to show this inequality that I can replace with look ahead prediction or look ahead output by the FTL, I'm gonna, so this part is common, the first part, right? FT of WT is common, so we can delete those terms. We'll see that we essentially want to show this property, that FT at the look ahead point, is less than or equal to FT at u for all u. So you fixed a particular point u, and here you are changing the points. At every round t, you're gonna take the point that you would have given in the next round as the point here, and you're going to show that this sum is less than this sum. So we're going to prove this by a very simple induction. So let's say it's true for t minus 1 rounds. So that is what I've written here. So till the only thing changes is this, and we're going to add ft of wt plus 1, capital T plus 1, to both sides. Okay, so the left hand side is what we want, okay, which is the same term here. And the right hand side has this additional term that we added. Because this inequality holds, due to induction hypothesis, for all u in S, we're going to set u to be equal to wt plus 1. Okay, and so the right hand side is going to be a sum of t terms, but evaluated at a single point, which is w capital T plus 1. Okay, but we know that w capital T plus 1 is essentially the minimizer of the sum of t terms of ft of u. Okay, that's the rule by which follow the leader is working, which means that you can just substitute any other point and you can only do worse. So in the sense you will only increase, and therefore this inequality holds. So we just proved the upper bound on regret, and we haven't yet used convexity. Do you think we have a regret bound on follow the leader? Not yet, because we only showed that the regret for follow the leader is a sum of t terms, and that's just almost the same thing as definition, except we just changed some quantities in there. Okay, so let's get some intuition for follow the leader through a couple of examples. Okay, so let's say now we're going to make a couple of assumptions. Let's assume nature prime chooses ft of w to be essentially these quadratic functions. So what is the dependence on t? The only potentially random or adversarial or whatever the thing is going to be this term zt. Okay, that which parameterizes that function of w. Okay, so let's say nature only picks functions like this. Okay, and in particular zt is upper bounded in let's say 2 norm. Okay, so that's I'm just trying to restrict nature to provide me only functions of this form. Okay, and follow the leader's choice you can see by just differentiating that optimization problem and setting the first differential to be equal to 0. You can see that this is the optimal solution. So you don't really have to solve the convex program. You can just take an empirical average of the t minus 1 terms, and that's the optimal solution of that convex program. So FTL's choice is just this. Okay. Then we can actually kind of now again evaluate ft of wt minus ft of wt plus 1 as follows. Okay. So this term is I'm just replacing the definition of ft. I know that nature is always going to give me some function of this form. The only thing I don't know is zt, of course. So let me just put this as the first term here. The second term is at t plus 1. So at wt plus 1, which is still evaluated at ft. So ft is just zt is just copied here. W is changed to wt plus 1, and you can see later, or that wt plus 1 is just a weighted average of the previous wt and the new zt. Okay, that you can very quickly see. So if you do this, then you're just kind of just use your regular algebra to see that it comes down to this definition, and then you can upper bound the coefficient term, which is a function of t, as equal to 1 by t. Okay. The second term you can upper bound by 4L square. That's because wt is always going to be less, in 2 norm is always going to be less than or equal to L, and zt itself is also going to be less than or equal to L. So potentially they can vary far from each other in terms of 2 times L. So 2 times L the whole square is 4L square. So you can kind of see from this algebra that this difference between, given a function, the difference between 2 successive outputs that the learner is generating is kind of bounded, and in fact the difference is decaying in function of t. Okay. So which if you put in the regret upper bound that we had, you can see that you can do the summation from t is equal to 1 to t of this 1 by t term. You'll get some little bit more algebra. It's log t. Okay, and so you can see that regret for this online convex optimization learner FTL, if nature chose this restricted set of functions, is 4L, some constant times log t. So at least now we can say we have some handle on the regret. Okay. So basically, look at the top point. FTL is doing great for quadratic functions if nature provides quadratic functions, and the intuition here is that averages are stable. The difference between wt plus 1 and wt, there's only one term, which is actually in fact divided by. We saw here that the difference between wt plus 1 and wt is that a little bit of rescaling of the previous term and one new term is added, which is actually divided by t. So you're not really changing your the sequence that you're generating too much in successive rounds, and that's kind of leading to something called stability. Okay, which means that the difference between wt and wt plus 1 is not changing, evaluated in this way, evaluated in terms of, let's say, the function ft. But FTL is going to fail for some other functions. If the nature generates some other functions, FTL is going to fail. So we can see that from this next example. So let's say our set is just the union is just the interval from -1 to 1. Okay, it's a convex set, right? Convex closed set. Let's say our ft of w, it's a function of w, is going to be just w times zt. Zt is just some scalar which nature is picking, and then maybe it's random, maybe not. Okay, we are not really assuming anything about how the nature is generating zt. Okay, and let's let the nature generate zt as this. Okay, zt is going to be -0.5 in the first round, and then alternates between minus and plus ones later on. Okay. You can see for this function by actually solving that minimization problem, which is very simple, that wt always chooses the corners of the set. The set is an interval from -1 to 1, so the sequence of choice of w's is going to be 0, 1, -1, 1, and so on. Okay. You can see that by just evaluating the minimization problem that FTL solves inside, which means that FTL is obtaining a cumulative loss. cumulative loss of t minus 1. So only in the first round it does fine, and in all other rounds it's suffering a loss t minus 1. And if you pick any other expert, any fixed expert, let's pick some expert, let's say u is equal to 0, it has 0 cumulative loss. Okay. That's because everything else after the first round is getting cancelled, right? Plus 1, minus 1. So you can see that the regret is actually lower bounded by t minus 1. So you can see that if nature provides certain types of convex functions, FTL is failing. Nature provides some other types of convex functions which are quadratic functions, FTL is succeeding. So, and the intuition again is that the WT and WT plus 1 are getting closer for the quadratic case, and WT and WT plus 1 are not really doing anything. They are just minus 1 plus 1, just staying there in every round, every successive round for the linear case. So basically, the understanding here is that FTL works because the set of functions that nature is providing is nature itself is providing some functions which are kind of allowing for stability of the learner. But we don't want to depend on the nature. So now we're going to improve that FTL algorithm and try to come up with stability from internally. So what we're going to do is we're going to add something that we call regularization of our own to stabilize. So what is this concept? It's very simple. It's just saying, okay, let me have another convex function which is a map from S to R. Let me just call this regularizer, and at every time t, my learner is going to choose WT, which is an argmin of the same thing as before, the previous t minus term, t minus 1 functions evaluated at W, plus I'll add a function which is psi of W. So essentially, if psi of W is 0 for all W, then FTL is just FTRL is just FTL, right? I just added an additional term in that subroutine where you're trying to pick W, right? Note that there's an important difference here in the use of the word regularization. In batch learning, regularization is a part of the objective. You are actually solving a convex. Let's say you're doing regularized least squares. Regularization is part of the objective. Okay. Here, regularization is something internal to your learner. Okay. The game is just you have to provide WT. You're getting functions. Okay. You can hallucinate about anything you want to pick a choice of WT, and in this case, I am just hallucinating that I want to put this function psi, okay, psi of W, and then pick my choice. So note that our objective is still the same as regret, same thing. So let's look at an example. Let's say FTs are linear, the same bad setting that was happening in FTL case, but I choose a quadratic psi function. Okay. In particular, let me choose psi function which is as follows. It's just a L2 norm of the W. So I'm just preferring W's to be 0 rather than anything else. That's the preference that is being indicated here. And FTs are just linear functions of W. So in the previous example, it was one-dimensional case. We can just go to the d-dimensional case without any difficulty. So let's say S is a subset of RD. Okay. So nature is still providing me linear functions, but I'm hallucinating about this. I have added this regularizer while computing my WT. The next line is just showing what's happening. So basically, this is the optimization problem explicitly, where so in round t, so I just kind of substituted f of I to be equal to W times Zi, and you can see that W kind of is common, so I can take the sum itself and I just call an internal parameter theta t, and you will have the same expression. I just substituted psi and f. You can see that W is trying to hold back, the first term is trying to hold and trying to regularize towards 0. The second term is trying to, direct me to move. Basically, this one looks like essentially is the negative sum of gradients, because if it's a linear function, the gradient of a linear function is just the coefficient vectors. So theta t is somehow kind of capturing a summary statistic about these gradients. Okay. Okay. So basically, what is the rule? So given this particular form of the regularizer that the learner chose, and given that we know that nature is only going to give us linear functions, we can actually don't have to solve this. You actually have a closed form solution for this minimization. That's what this first point is showing. In particular, if the set S is the whole RD, then you can do that minimization by just keeping track of the previous point that you picked, and when the nature provides that function f of t, you just take the zt part of it and just add it or subtract it to the previous point that you suggested. So you don't really you're not really solving an optimization problem. You're just keeping track of the previous suggestion that you made, previous WT that you picked, and you're getting the input from nature. This looks like gradient update, okay. And if S is not the RD, then you can do some projection. So let's not go into that, and it's very similar, okay. But the question is, what can we say about the regret of FTRL? We wanted a kind of a regret bound. We saw that follow the leader, when nature was providing quadratic functions, had a nice regret bound. We want a case when nature is providing linear functions and we introduce the regularizer to have a nice regret bound as well. So that's this theorem here, which says that if the set is convex and we have linear functions being provided by nature, which is of course convex functions, and we chose this as a regularizer internally, which is the choice by this algorithm FTRL, then the regret is upper bounded by a sum of two terms, okay, and eta is a parameter of that regularizer, okay. So you can see that okay, I had a summation over t terms. I still have a summation over t terms here, but let's look at what eta is trying to do. I really haven't shrunk too much, but let's see what eta is trying to do. Eta is trying to trade off bias due to regularization and variance due to changing ZTs. So if ZTs change all over the place, if nature is being very even while providing linear functions, it's kind of varying the linear functions all over the place. It's providing a ZT parameter from one end and another ZT parameter from another end. So this is going to vary a lot because there is sum over t terms. But if you choose eta small, then you're kind of limiting this term. Okay. But if you choose eta small, you're kind of you get a high penalty in terms of this term, which is when you compare your regret with respect to a fixed point u. If you choose eta small, you're actually kind of incurring a huge term here because you're not going towards u. So ideally, your regret would be small if your choice of WT points would somehow converge towards u, okay, because that's the comparison class. For example, u could be the global minimizer of in that okay. In the convex optimization case, the u was w star. That's all I'm saying. Okay. So basically, you have a regret bound which is a function of eta and some norms on the points in your set S and norms on what nature can do. If you assume some bounds on those norms and pick a particular eta, you can see that the regret is actually sublinear in T. Okay. So this is actually one of the first regret bounds we have for online convex optimization. We have a sound algorithm which is follow the regularized leader, and we have a regret bound for that algorithm which scales as root t. So essentially it's saying that average regret, which is if you divide both sides by t, goes to 0 as desired. It is not as fast as quadratic functions. In quadratic functions, we saw that the regret was upper bounded by upper bounded by log t term, 4l times 4l square times log t term, right? So here it's not that fast. Root t, log t, there's a difference. Okay, and we are not going to show proofs from this point onwards, which is good that only 10 minutes left. So FTRL was an algorithm when we were doing this regret analysis, we kind of said, okay, nature is still limited. It can only provide linear functions, okay, to us, and it makes computationally easy as well because we knew how to. We only had to keep track of the previous WT to get a WT plus 1. We didn't have to really solve the convex optimization problem as a subroutine of the FTRL. Okay. The next algorithm, which I'll quickly just describe, is called the online subgradient descent, or OGD for short. Here you can deal with. You don't have to restrict nature to linear loss function. So nature can pick any convex loss function, and essentially it's the same as FTRL, but what we're going to do is we're going to, since it's a convex function that nature provides, we're going to do a linear approximation of that convex function and use the subgradient. Okay. So basically, it was a convex function. It was a non-linear function. We linearize it, okay, at the t point, and use that in our use the gradient of that function to estimate Wt plus 1 that we are going to provide. So basically, this is the algorithm. It's almost the same as FTRL. So we want to predict Wt. We predict Wt. We receive a function Ft. We're going to pick a subgradient. It could be just gradient if the function is differentiable at the Wt point, and then just use Zt as the update of our Wt plus 1 term. Okay. We had the same update rule actually in FTRL, but yeah, so the same update rule, except that we're going to pick a particular Zt, which is derived from Ft. So online subgradient descent is nothing more than FTRL on quadratic regularizers and linear subgradient approximators of Ft. Okay. So to bound the regret of online subgradient descent, we're going to use convexity. So this is till now we did not see actually much of convexity. We saw, okay, what is some notion of stability between f of t of w minus f of t of w plus 1. That was kind of the notion that we saw. The final part of this is that convexity can give us a very quick bound on the regret of this online convex optimization learner. Okay. So and it's just a one-line proof. Okay. Recall, when we were doing when I was studying some regret for FTRL, I said, okay, let's restrict to linear functions being provided by nature, and let's pick a particular function which is regularized in this way. Then we know that regret is upper bounded is a root t term. Okay. For online gradient descent, we said, of course, for online gradient descent, we have to still bound regret, and this is the definition of regret, if you remember. By convexity, we know that so f of t is a convex function, which means that f of t at any point u in the domain is lower bounded by a linear approximation at that point at any. So fix a point Wt. Remember the original picture that I had drawn, a convex function. Pick any point w. At any other point u, wherever you pick, this linear approximation is going to be a lower bound for that function, right? Function evaluation or the function value. Okay. So just I am just reordering the terms. So f of t of w minus f of t of u is going to be this term flipped. Okay. So Wt just came forward and u went backward. So we have this property, okay, from convexity. So from here, do you think you can complete? I mean, you can think of why we can get a very quick regret bound for online gradient descent. Does this look like the term in the regret bound for follow the regularized leader? So this, you see, this is the term in the follow the regularized leader. If nature was playing linear functions, right? Same term. And we know that if nature was playing linear functions, then we have this as the bound, BL times square root t. But we know that each term is upper bounding a term which we actually want to bound, right? So the regret bound for OGD will have this as the term, which is the left hand side here, right? So bound we got for linear function loss applies directly for OGDs for general convex functions, and in fact this is it. There is no other proof. So OGD is the first practical non-toy algorithm we have developed. So basically OGD can work for all convex functions. Basically it's just saying, okay, give me a convex function. I'm going to just take a linear approximation and then figure out how to suggest the next update, right, WT plus 1. But the analysis for the regret of OGD just follows from FTRL, because since we are using convexity property, we see that the regret of FTRL is upper bounding the regret of OGD, and therefore we get a regret of essentially BL square root T. So yeah, so that point is not very important. So let's look at a very simple example just to so given this OGD algorithm, we can quickly come up with a regret bound for an online SVM setting. Okay, so what is the online SVM setting? The only thing the online SVM setting is going to borrow from your regular SVM is going to be the loss function. So let's say XD is belongs to RD, and you have a binary class. So your FT function is going to be a max of 0 and 1 minus YT times W transpose XT. So this is the hinge loss. Okay, so nature is going to nature is essentially generating YT and XT. So given YT and XT, you can always, FT is parameterized by YT and XT, so therefore you'll get this function. So nature is essentially providing you this FT function, and your algorithm is as follows: if YT times WT transpose XT is greater than or equal to 1, do nothing, and if this is not true, then you update your parameter which parameterizes your SVM. Okay, this comes from the same update rule that you had for OGD. Then you can say that you have a regret bound which is less than or equal to BL times square root T. So okay, so in the last 4 minutes, I'm going to quickly talk about something called multi-arm bandit. Okay, which is, I'm not really going to go into any algorithms. I'm going to just say, okay, we thought about online learning, thought about online convex optimization, which can potentially be called as a subroutine for online learning settings. What is the I've also heard of some multi-arm bandit. What is its relation to this tutorial that we just went through? So basically, in online learning, let's think of expert advice. So which means that let's still think of finite number of experts. Okay. Basically, remember the first problem that we had. We had, let's say, D experts, and we were picking an expert. We were picking an expert and just following what the expert's predictions are. And nature was revealing a loss which was a loss for all experts, because in the online learning setting, let's say you picked an expert I, you made the prediction PI, which corresponds to the expert I. Nature provided the ground label, YT. You can compare all the predictions. So you had D experts. You can always evaluate what the D predictions were and see whether YT matches to any of these predictors. So you kind of know what other experts would have done if you had applied them. But you can't really do that, in many settings. Like for example, clinical trials. You can't give a medicine and figure out what would have happened if medicine was not given. Or for example, in advertisement placement, you can't figure out what would have happened if you did not put the advertisement, right? Or if you had put some other advertisement, you wouldn't know. So we only observe essentially some feedback about the prediction that we made, okay, or the action that we took. Okay, so this is the essentially this is called the partial feedback setting, and also essentially called the multi-arm bandit setting. It's definitely more difficult because in each round you are getting less information. You're only getting information of what you tried, okay. Whereas in online learning setting, you can get information of what you did not try as well. So to incur less regret, you have to do something called explore actions that you did not try and exploit actions that you tried. Okay. So the reason why this is the last part of online learning is because we saw online gradient descent, which we just saw a few slides ago. It's a online learning. It's an online convex optimization algorithm. We picked the regularizer to be a quadratic regularizer. Now we can change that quadratic regularizer. Let's trash it, and let's use what is called the entropic regularizer, which is slightly a different function, which is just instead of norm of W square, it's not instead of norm two norm of W square, it's just the sum of Wi log of Wi. Okay, that's it. We change that, then you will see that the update rule is going to be something similar to what is called the exponential weights, exponentiated gradient algorithm, or the hedge algorithm, or the exponential weights algorithm, where it's again an online learning algorithm. So where so in each round you take one of the experts action, nature reveals the laws for all experts, and you kind of the next suggestion, the next WT plus 1 that you're going to pick is just WT times e to the power minus loss that you incurred. So you kind of downweigh and upweigh W's as you kind of play this game in the online learning setting. The way it's related to multi-on band setting is you can use the same algorithm, this exponentiated gradient algorithm, in the multi-on band setting by just making two modifications, which is that you get a loss, which you only get one loss for the action that you took. You have D actions, right? You kind of, from that single feedback that you get, you somehow create a D-dimensional vector. Okay, so there are some details here, but let's say you kind of somehow given a single coordinate, you got all the coordinates. Then you can just use that in that online gradient descent method where I change the regularizer as well. And then to really explore, you also want to explore actions you did not to use an experiment, you have to give some offset to each of the W's that you have, and that is the famous EXP3 algorithm for multi-on band setting. So basically, online learning with a few changes could give you a candidate algorithm which can work in the multi-on band setting, where this algorithm also enjoys something called regret in the multi-on band setting, which we did not discuss here at all. Okay. So that's it. So any questions or statements? Yeah. Yeah, so the tools that we use were just undergrad probability and very elementary properties of convexity. So that way we haven't even really looked at anything, no distributions, nothing. So this is one of the simpler algorithms to analyze and as well as come up with in the online world. Okay, that's it. Thank you.